equals the PO2 of the alveoli. Well, okay, the partial pressure is equal. Well, the main idea with this that we emphasized the other day, and it's kind of a, that cells need 20 milliliters of oxygen per 100 ml, not 0.5. 0.5, their cells will be starving for oxygen. That's what that translates to. So we come on down with this just a little bit, and we say, then here's what you need to definitely memorize right here. Make sure you highlight that. I think we talked about this the other day, and I can put it on the, I can put this on the big screen up here like this. I'm going to get over to my little deal up here. Put this like this, and just kind of come down a little bit. Make sure you learn this. Remember when I had physics, there were certain formulas we had to learn, memorize. Hated memorizing formulas like that. Had to memorize certain math formulas, type formulas. Just remember that 1 gram of hemoglobin carries 1.34 mLs of O2. And on the average, there's 15 grams of hemoglobin per 100 mLs of blood. So your grams of hemoglobin, if you're low, and the question you were asking me, I think, had something to do with the amount of hemoglobin.
Yeah, because like when I did my blood work,
yeah.
So like an average, it's supposed to be between 12 and 16.
Yes.
So like we started at 12, that's way
right.
under
That's kind of low. You know, 12. It said 12 or 16.
It said between 12 and 16.
Yeah.
Mine was like 13 point something. So I was still like in the 18 range.
Yeah. So
after you multiply by the 1.34.
1.3. Yeah. So in other words, yeah. When he was up out, now I see what you were talking to me about. Yeah. So you could have experienced a little tiredness, maybe. I don't know. Did you? Yep, not really. 18 so close to
it was like
20.
High 18.
Yeah,
so.
and you know,
but
you're so close to 20. The normal
range was 12 to 16. Like 12 would be.
12's pretty low.
Yeah.
12's pretty low, yeah. All right, but anyway, there's 1.34. Therefore, 1.34 mLs per gram times 15 grams, that gives you 20.1. 20.1 mLs of O2 per 100 mLs of blood. Well, that's good. You know, that satisfies. We're not trying to break any records, but that satisfies the cell needs. So the tissue needs. So they keeps everything happy, keeps everybody happy. All right. So now one of the things, and this is just some hoopla right in here. It's just a matter of reading over it. What causes the oxygen to be released from hemoglobin? In other words, what causes hemoglobin to give it up at the tissue level? Well, there are a couple of things. The low PO2 at the tissue level, that's a factor. Acid is a factor. What acid? Lactic acid, carbonic acid, those acids. So right here, and this is just saying that the tap side is no longer free gas, doesn't affect the partial pressure. PO2 is the most important factor, determines how much O2, in other words, PO2, how much combines with oxygen. There's oxyhemoglobin, we talked about this the other day. And right here, when blood, now, okay, low O2, oxygen separates from hemoglobin at the low O2, low PO2 level at the tissue area. Then the oxygen is low, so this facilitates hemoglobin giving up the oxygen, so that's cool. That's interesting, that's good. All right, acidity, HbO2 splits when placed in an acid solution. What acids? Carbonic acid is one which we'll talk about in a minute. When we talk about carbon dioxide transport, we'll talk about carbonic acid and how that comes about. Carbonic acid, and also in our 2401, we're talking about muscle contraction. And we finished muscle actually. But we have been talking about muscle in 2401. And in 2401, you know, there's a certain amount of anaerobic contraction stuff that goes on. And when converting glucose to pyruvic acid, in the absence of oxygen, pyruvic acid is converted to lactic acid. A little bit of that's going to be done always. You know, there's going to be a little bit of lactic acid. And so the lactic acid also facilitates this splitting. That's another factor. Lactic acid from muscles contributes to that. And then I have Niels Bohr, B-O-H-R. He was a physicist. And in an acid environment, it's just reading this, it's just some fluff. Just Niels Bohr. In physics, you would deal more with his stuff, the Bohr effect. But it's just in an acid environment, oxygen splits more readily from hemoglobin and so forth. In other words, in an acid, the H plus ions alter the structure of Hb and it decreases its O2 carrying capacity. You don't need to memorize that at all. It just, in an acid solution, oxygen is given up from hemoglobin. That's the main thrust of this. So what are a couple of factors? Low O2, acidity, and then there's one more of these, temperature, that I emphasize, metabolic. In other words, when you do stuff, you walk around, the temperature in the muscles is going to elevate a little bit, and that increase in temperature will also cause blood to give it up. That causes the hemoglobin to give up oxygen. So that is another, that's just a fact. So much for oxygen transport. Oxygen transport. So much for that. Oxygen attached to hemoglobin. I think from our standpoint, the hemoglobin level is very important. You know, your low hemoglobin, anemia, that sort of thing. So, that's important. Carbon dioxide transport's a little bit more difficult. You have a handout sheet on it. The handout sheet you have, and I had to keep one. I have to just have one more of these in here, so I have to keep one of them. But this is actually in your pages of notes. I don't know if this diagram is in your pages, and that's why I gave you a handout on the oxygen, on the carbon dioxide. All right, CO2. We can't handle CO2 buildup. CO2 buildup in the blood is called respiratory acidosis. People with chronic bronchitis and emphysema and so forth will get it. The CO2 levels will get out and in. And that is the respiratory acidosis situation. All right, now, carbon dioxide is carried in several ways. CO2, carbon dioxide. Is carbon dioxide classified as an organic or an inorganic molecule? Inorganic, right. It's classified as an inorganic molecule. CO2 is. All right, and you and I have to deal with it. We've got to get rid of CO2. This is all. It forms in, all right, in plasma. How is carbon dioxide? This was on, I took a medical college admission test many years ago. A long time ago, I took an exam. And this is one of the, there are a couple of things, a couple of questions on that exam from this information we're talking about. One of them was, how's the majority of hemoglobin carried, how's the majority of carbon dioxide carried in the blood? And the answer was, as a bicarbonate. And that was one of the questions on this. And another question on there had to do with the concept of the term chloride shift, which we'll talk about in a few minutes. So right in here, plasma, about 7% is dissolved in plasma. So a small percent of it, of CO2, is just dissolved in blood plasma. What is blood plasma? That's the liquid part of blood. So everybody pretty well on that one. All right, now right here, protein part of hemoglobin, about 23% combines with the globin portion of hemoglobin. What is hemoglobin made up of? Heme. What does heme contain? What's chelated? Iron. Iron, and the globin is the protein part of hemoglobin, the globin molecule. All right, so about 23%. And then the majority of it, this is the question. So there's oxyhemoglobin right there, or carboxyhemoglobin right there, Hb plus CO2. That's carboxyhemoglobin is what that's called. And the above is influenced, that just tells you some fluff there, influenced by the PCO2 for the hemoglobin attachment. PCO2 is high in the tissue capillaries. This encourages the carbamino hemoglobin, as I said, carboxy or carbamino hemoglobin. That encourages that at the tissue level. So there's not that you'll even have to recognize that. You won't have to recognize that at all, but there that is. All right, now, in pulmonary capillaries, PCO2 is low and CO2 readily splits apart. It mainly has to do with the pressure difference at the tissue level. And the CO2 splits apart from the globin and enters the alveoli and so forth by diffusion. That's, so in the pulmonary, in other words, when we exhale carbon dioxide, it's carried in the form primarily, now right here, in the form of a bicarbonate. In other words, about 70%. And this is a question that will come up probably on a standardized exam. How is the majority of carbon dioxide carried in the blood? It's carried primarily as a bicarbonate, and specifically sodium bicarbonate is the way it's carried. So this is one that you'll see a lot.